All right, so the maximal likelihood estimation and then make it more general, like this kind of probability-based formulation has a very fundamental role in the machine learning nutshells. And the most important is it provides almost the mostly used scoring function, which you're going to learn in the deep learning. So all those cross entropy based laws, and later yeah, it's just so important. All the most popular classification loss function is based on the maximal likelihood estimation. So that's why I want to talk about it first before we jump into any of the classification algorithms. And later, I'm going to introduce a little bit probability-based representation, mostly naive-Bayes models, after we finish the deep learning, after we finish the boosting trees, and when we talk about text, one-dimensional data. So this section 2, primarily we focus on imaging data, the two-dimensional grid type of input imaging data. Okay, so review. So I put probability as prerequisite, but I think some of you still need to learn a little bit. So I highly recommend you to go over my old slides. So I hope you understand. Sorry. So what is event space? What is random variable? What is germ probability? What is marginalization? What is conditional probability? What is chain rule? What is Bayes rule? What is law of total probability? And later, we're going to use some of the very important structural properties called conditional independence to design this called the naive-Bayes algorithm. But today, I will just do a really quick review. If you're not very comfortable with this, go read out my slides and read some, maybe Khan Academy or MOOC, some kind of open courses, basic course. Okay, so let me review. So what is sample space? What is event? So sample space in the probability sense is, sample space is the set of all possible outcomes. So for example, your event is you toss a coin twice. Then your sample space is HH, HT, TH, TT. So I hope this is kind of self-explained. And then what is event? Event is a subset of that sample space. So for example, an event can be first toss is head, which means what? There's only two. It's a subset out of that size 4 set. And in my current set, it's HH and HT, which means the first toss is a head. And then S is called an event space. So S is just a set of all possible events. And it contains this special events like empty event and the whole event, which is the O. All right, so, and then the really important is from the event into the random variables. You can think about random variable is just a function. So it's a very, random variable, it's a very concise way to specify the subsets of your sample space. A possible event space. So again, what you have O and possibly, and the events can be grade A students, assuming my O is all possible students. And then the first kind of event can be grade A student, grade B student, hardworking student. And then I can just design a function H. If H equal to yes, student work hard. And I don't need to write this really long, hard-working student and write every possible student and build a subset. I don't need to do that. I only just write PH. And that's exactly what his random variable is doing. This H is this random variable matched things from my my space, from my sample space into a yes/no. It's more like a selection. So I selected into my subset or not selected into my subset. And this H is a random variable. It's essentially got a subset from the O. Yeah? it builds an event in the end. So that's just the basic idea of random variable. I hope you still remember from your probability class. And when we talk about random variables, I mean, we talk about most likely is the true and joint probability. So when we talk about, like for example, we treat input as X, output as Y, and we care about joint probability, it's just P, X, and Y. Marginal probability is Py conditional on X. Yeah, so for example, in our current notation, Pxy is joint probability, Py conditional X is conditional probability, and it's marginal probability. Px is conditional probability, and Py conditional X is the conditional probability. So when you can't directly estimate those from the data, and there are certain rules you can use, right? You can use chain rules to estimate joint probability. You can use total law of probability to estimate marginal probability. You can use Bayes rules to estimate conditional probability. All right. So this is the general guidance you normally use. So if I cannot directly estimate that specific probability from data directly, then let me use this kind of rules to calculate it from other possible probability that can be directly estimated from the data. All right, so this is a concrete way to show you what is chain rule, what is the marginal probability law function, this law equation, and what is Bayes rule. And I hope you still remember what is Bayes rule. And so PAB equals to PB times PA conditional B, and this is very elementary. PB equals to PB A plus PB not A. All right, so this is just very classic. How do you, assuming you can estimate PBA easily from data, you can also easily estimate PB not A from data, and together you can estimate PB. So that's how you do it. And then Bayes rule, just classic. It is hard to estimate PB conditional A, and it's easy to estimate PA conditional B, then you use Bayes rules, and then to calculate PB conditional A using PA conditional B. Okay, so that's just, it's very classic elementary probability rules. And you can also have this Bayes rules for more variables. So you can do P, X conditional Y, and Z, and this is the more variable Bayes rule you can use. So later you're going to realize how we're going to use it in a nice Bayes models. Yeah, but for now it's just more like a flash that you just kind of just quickly get into your memory. Give you examples. What do I mean? I mean to get joint probability. Okay, so assuming we have a box with 3 red balls and 1 blue ball, you cannot tell what are those balls because they're black box. Okay, now we just draw from this box, and this is the sequence we get. We just draw, well, we first got R, so okay, this is actually the other. So we can write it as R, and B. So then I'm asking you, what's the probability of drawing 2 red balls in the first try? So you can think about draw the red ball at the first try. It's a random variable, that's my B1, and draw the red ball in the second try, it's my B2, and then essentially you are trying to get PB1 and PB2 both equal to R. How to calculate this? This is actually not easy to directly estimate from this kind of data, but you can do joint probability kind of calculation. I have in my review slide, feel free to check it out. And the conditional probability, for example, I just ask you, what's the probability to your second draw is a red? Yeah, so how to get it? So you have to consider the first draw in this case. And you need to consider all the possible draw cases from the first draw, and then to calculate the PB2 equals to R. So this is exactly the rule of total law of probability. Yeah, so this sounds very dry, but when you have a concrete example, it's actually very easy. You're going to understand very easily. Okay, so enough about review of probability. Let's talk about maximum likelihood estimation. So what is basic maximal likelihood estimator? So why do I talk about it? The reason is this is a very important scoring function, and then you're going to use it to score later. In fact, is the y versus the y predicted versus the y truth. And this is one major scoring function we actually for scoring the differences of y and y hat in the classification case. All right, so keep that in mind. Everything learned here, it's for the classification purpose. But for now, I mean, there's no classification model. It's just a probability model. So we are observing, so I hope you still remember, so when you have a random variables, that's just a random variable, right? And you're going to have observed observation for that random variable. Because random variable is stochastic, right? So assuming my random variable is z, and I actually observed many of that z. So assuming, let's just make an example. So I'm toss a coin, and that coin flip, right? So I can just see this is a z. This random variable is a Bernoulli random variable, and in fact, it's a binary. There's only two possible values, head and tail. All right, so if I just keep tossing and different times of tossing, not relevant to each other at all, they're all independent to each other. I toss 1, 2, 3, 4, and I'm just remember that tossing results. So this will give me an observation like z1, z2, assume I tossed n times zn. All right, so this is my observed observation of my random variable z, Bernoulli distribution. And we actually know Bernoulli distribution has a parameter p, so heads up, the probability of head is up, it's probability p, right? So normally you write this probability as 1 p and 1 minus p. I hope you still remember how we represent Bernoulli distribution. All right, but I actually do not know p. I don't know p. I do not know what's the probability of the heads up, but I observe z1, z2 onto zn. So the whole task is I'm trying to use z1, z2 onto zn to help me estimate the best p. And this means this essentially it's about estimating parameter from data through a probability formulation and using this probability. All right, so here the theta, so consider a sample set, in this case z1 onto zn, it's just all those draws, right? So highly likely this may look like h, maybe t, and then so on, ht. It's just a set of head and tail outcomes, right? And I want to use that head and tail outcome to help me estimate the best p that describe my data. So this is exactly what the maximal likelihood type of estimation can solve. And so what do you solve? So essentially I'm trying to write down, because I can represent the pz, right? Each sub zi, I have a probability. And each toss is independent from each other. They're not relevant. When you have so many, you have pz, so this is joint probability. And they're not related to each other. So when all those pz onto the n not related to each other, I can just their joint probability equivalent to each probability, then multiply together. And that's gave me this representation. Then my whole goal is to argmax. So my theta best, it just maximize this. And this is actually called data likelihood. And that's the reason why this whole formulation is called maximal likelihood estimation. All right, so if you have questions, just put in the chat, and we're just maximize the likelihood. The likelihood is just the probability observing all of the z1 until zn. Observe the set. I'm trying to find the best theta that maximize the probability of this set, observing the set. All right, so how do you do it? You just assume there's a particular model with unknown parameter theta, and then you define this probability. You use that theta to get a formula, parametric way to write down the probability of each observed di. And then you put, because you observe a set of those, right? And then you just put them together, and it's just trying to maximize and the way you put them together, which is just theta is the argmax that maximizes the strong probability. And so we normally actually, in fact, not directly work with the pz1 until zn given theta. We work on the log version of this. So this is called log likelihood. And which is this. I mean, the reason is probability are all within the 0 to 1 range. When you multiply it, when you have a large n, you multiply so many smaller numbers all together, just all smaller than 1, you're going to have the numerical floating issues. So if you take a log, so that's dramatically reduced of those kind of numerical problems. So that's why we normally actually truly, when we do the argmax, we work on the log likelihood quantities. So our theta best is the one actually argmax this log likelihood. All right, so yeah, this is exactly the procedure called maximal likelihood estimator. And in most cases, this scoring function is both consistent and efficient. So it's a good scoring function. So how to estimate the Bernoulli probability P from observed data using maximal likelihood estimation.